Okay, today's video is very related to what we learned in our last video in 2.1. We're still going to be talking about local extreme values and things like that, but we're going to look at how can the second derivative help me out? Where is the second derivative useful? So let's think about what we know about the second derivative. So far, all we know about the second derivative is that it's related to acceleration. But that term acceleration is very much, it's just for that physics application, right? It's for a very specific context. So can I somehow generalize this? What is it? If I just think about this in terms of general math, what does the second derivative actually tell me? Well, to help us, let's think about a car accelerating or something accelerating and think about what would the graph look like for an object that was accelerating. Well, I'd be starting slow, but then if I'm accelerating, I would move faster and faster and faster, and my graph would get steeper and steeper and steeper, right? What it gives me is a curved function. If you think about a linear function has no acceleration. It's staying at a constant rate, okay? So what does that tell me about the second derivative of a function? The second derivative tells me about the curvature of the function, okay? How the function curves. Specifically, it tells me these two things. If my second derivative is greater than 0, so if my second derivative is positive, what does it tell me? That tells me that my function has an upwards curvature. So in this case, with acceleration, if I'm accelerating, if I'm speeding up, I have this upwards curvature. And I can see that with a positive second derivative, okay? We call this concave up, okay? And I'll put in parentheses here, upwards curvature. To help you make sense of it. It means my function is curving upwards, okay? And then similarly, if my second derivative is less than 0, we call that concave down, okay? Where my function has downwards curvature. So this is a good example of concave up. If I were to just graph a quick example of concave down, right? Concave down would look something like this, okay? Or even something like this, right? Anywhere where I see that downwards curvature is considered concave down. Okay, so that's what the second derivative tells me about a graph for any situation. It tells me about the curvature. So how does that help me if I'm thinking about this idea of minimums and maximums? How does knowing the curvature help me with minimums and maximums? Well, let's look at an example. Okay, let's look at an example. Let's let f of x equal negative x cubed plus 6x squared minus 17. And what if I wanted to find the local extrema, right? Local minimums, local maximums. Well, we learned about this in our last video, right? What I'll do is I'll take the derivative, negative 3x squared plus 12x, and then derivative of 17 just goes to 0. What am I going to do with that derivative? I'm going to set it equal to 0 and solve, right? This is going to tell me the critical points, the points where I could have a local minimum or a local maximum, okay? I can factor, so I can factor out a negative 3x, and I'm left with x minus 4. If I set that equal to 0, that gives me two critical points of 0 and positive 4. Okay, so I have two critical points. Now, normally, using what we call the first derivative test, I could go ahead and make a number line, put my critical points on the number line, right? I'll just make my number line, put my critical points on the number line, and then test these intervals in between, right? To see if my function's increasing or decreasing. But why don't we try to use the second derivative? That's what this section's about. So let's see how the second derivative helps me. If I calculate the second derivative, since I'm still just working with a polynomial, it's not too complicated to calculate. I get negative 6x plus 12. That's my second derivative. Well, take a look at what happens when I plug in my critical points into my second derivative. Consider this. What is f double prime of 0? So what's the value of my second derivative at 0? I get negative 6 times 0 is 0 plus 12. I get 12, which is a positive number. What does that tell me about my function at 0? So it tells me that at x equals 0, f of x is concave up. My function has upwards curvature. Okay? So let's connect the dots here. I know I have a critical point. I have a possible minimum or a possible maximum at 0, but my function is also concave up. What does that mean? If I think about a graph, right? I know I either have a minimum a maximum or a minimum, right? One of these two options is true because I've got a critical point. I know I have a critical point here. But based on the fact that my function is concave up, which one does it have to be? Which one of these curves is concave up? This one is. The minimum is concave up. Maximums will always be concave down. And minimums will always be concave up. I guess maybe I should be careful with the word always because we have those situations where the derivative is undefined, which means the second derivative is also going to be undefined at that point. Okay, so we do have to be careful. So maybe I should just get rid of that word always, and we'll just stick with that statement. Maximums will be concave down. Minimums will be concave up. Okay. So this tells me right here that x equals 0 represents a local minimum. We did it using the second derivative to help us. So I can do something similar. I can test out my other point too. Let's test out 4. My other critical point was 4, right? So let's plug in 4 into my second derivative and see what my concavity is. Okay, so let me plug in 4. I get negative 6 times 4 is negative 24 plus 12 equals negative 12, which is less than 0. So I'm concave down. What does that mean? It's a maximum. Since it's a critical point and my concavity is downwards, right? Downwards curvature, x equals 4 is a local maximum. Okay, so just to review, what have we learned? We've learned that if if f prime of c equals 0, what does that tell me about c again? That means c is a critical point, okay? So pretty much if c is a critical point, And the second derivative of c, the second derivative of the function at c is positive. What did we decide? This represents a local minimum because I have that upwards curvature. Then f of x has a local minimum at x equals c. Okay? Similarly, right? If I have a critical point and the second derivative at that point is negative, then I have downwards curvature, which means I have a local maximum at the point. Perfect. So we call this the second derivative test, because you're using the second derivative to test your critical points, to test to see if they're local extreme or not. So we've talked about how the second derivative can help us determine minimums and maximums, but I want to revisit this idea of how does the second derivative help me, or what does it really tell me? So to help us out, at this point, knowing what we know about the first derivative and the second derivative, we can now answer the following 7 questions. Okay? So, the first and second derivative can help answer the following 7 questions about any function. Okay. Question 1. Where is the function increasing? Okay, think back. Which derivative helps me with this? The first derivative. The first derivative can tell me where the function is increasing. Similarly, where's the function decreasing? Okay. What's gonna, if you think about it, right? What's gonna separate these two intervals, or an interval where I'm increasing, an interval that I'm decreasing? What's gonna separate it? A local max or a local min, right? A critical point. So the first derivative will also help me find maximums. And like we just said, the second derivative can also help you out with this. It'll also help me find minimums. Okay? And let me just to remind us, right? These are considered critical points. But what else? If I get into my second derivative, then once again, oopsies. The second derivative is all about curvature, right? So the second derivative can help me figure out where the function is concave up, as well as where the function is concave down. And last but not least, the second derivative will also show me inflection points. Well, what do I mean by inflection points? Okay, inflection points are similar to critical points in that they represent where the concavity changes. An inflection point is where my function goes from being curving upwards to curving downwards, or the other way around, going from curving downwards to curving upwards. It's where the curvature changes. Okay. So these are the 7 pieces of information that that derivatives can help me find. Okay, so for a lot of the questions on your homework, it's going to have you go through all 7 of these items. Find where the function's increasing. Find where the function's decreasing. Find the maximums, minimums. Find where it's concave up. Find where it's concave down. Find any inflection points. So let's try it out. Let's try it out on a problem. Okay. Okay, consider the function. Oopsies, not sure what happened there. Consider the function x times the square root of, 4 minus x squared. Okay. So what we're going to do is we're going to systematically answer these 7 problems. And we're going to do this without a graph. The reason why we don't want to rely on graphs is because graphs can give you a rough idea of where things happen, but in order to get exact values, we need to be able to do it algebraically. So we're going to answer these 7 questions. Now, before we get started, though, we need to recognize that this function has a limited domain. I can't plug in whatever number I want because I have a square root. So first off, let's make sure we recognize what the domain is. What numbers can I actually plug in here? Well, the square root has to, whatever's inside the square root has to be positive. Has to stay greater than or equal to 0. So if I solve for that, that tells me that x has to be between -2 and positive. Okay, so there's my domain. I'll write in interval notation. I'm only looking at x values between -2 and 2. That's going to help me out a little bit as I get farther down the road. Okay, so let's answer these 7 questions. Increasing, decreasing, maximum, minimums, concave up, concave down, inflection points. How do I want to start this? Well, the first 4 all depend on what the first derivative is. So, first step, find the derivative. Okay, this is going to require me to use product rule, right? I've got a function. I've got a function here. I've got a function here. But what's also going to help me is rewriting this. Do yourself a favor and rewrite the square root as to the 1/2 power. Okay. So now there's my 2 functions, and when I my first function is just x. My second function is this 4 minus x squared to the 1/2 power. I need to take the derivative of both. F prime is just 1. G prime requires the chain rule. I get 1/2 4 minus x squared to the -1/2 times -2x. -2x is the derivative of my inside function, right? It's the derivative of 4 minus x squared. And I know I tell you a lot to not simplify, but I am going to simplify this because we're eventually going to take the second derivative. So the more simplified I can get it, the better. So this gives me -x over the square root of 4 minus x squared. Okay. If you have questions about that simplification, shoot me an email. Okay. So put this together, and I have x. I'm going to multiply these 2 pieces, x times -x over the square root of 4 minus x squared. And I get -x squared over the square root of 4 minus x squared. Plus, now I'm going to multiply those 2 together, which is pretty simple. That's just, square root of 4 minus x squared, right? I put the 1/2 back as a square root. Okay, there's my derivative. Now, I could go ahead and start plugging numbers in to see where my function's increasing and decreasing, but it would be more helpful to know first where the intervals are going to change, or where the intervals could possibly change, right? What points, or where if my function is increasing over a certain interval, where could it change to then decreasing? Well, it turns out these special points where I could potentially change are just my critical points. So, like I said in the last video, get used to this same start for so many of these problems. Take the derivative, set it equal to 0, right? I'm going to set this equal to 0 in order to find my critical points. Okay, so I have negative x squared over the square root of 4 minus x squared plus the square root of 4 minus x squared equals 0. How do I go about solving this? Well, let me go ahead and subtract the square root of 4 minus x squared over to the other side. What's nice about that is I now just have a fraction on the left side. And I never want variables in the denominator. So I'm going to go ahead and multiply both sides by the square root of 4 minus x squared. Okay. On the left side, this cancels out with the denominator, which is why I did it, and I'm left with negative x squared. But on the right side, what happens when I have square root of 4 minus x squared times square root of 4 minus x squared? I get the square root of 4 minus x squared squared, right? Two of the same thing multiplied together, I can square it. Well, what's the square root times a square? These two functions cancel out. And so I'm just left with negative x squared equals 4 minus x squared. Now I can finish by adding x squared onto both sides. And I'm left with 2x squared equals 4. I'll divide both sides by 2, then take the square root of both sides. And I'm left with these two possible critical points of positive root 2 and negative root 2. Right? Because whenever I take a square root, I have to recognize that both the positive and the negative could be options. So those are my critical points. Root 2 and negative root 2. Okay. So now I need to decide, well, actually, before I decide whether maximums or minimums, I just need to find my intervals where I'm increasing or decreasing. I can now go ahead and make my number line. Now that I have my critical points, I can make my number line. So let's come back up over here, and I'm going to make my number line. Now, this number line is going to be interesting because I'm not going to put arrows on either ends because I already know that my domain's limited. I'm only going between negative 2 and 2. But I'll go ahead and put my critical points on this number line. So negative root 2 and positive root 2. Okay. Well, perfect. So now my next step is really killing two birds with one stone, because I can go ahead and check these intervals to see if they're increasing and decreasing, and that will also help me decide if these critical points are minimums or maximums. Okay, so let's pick points in between. Let's start with the easy one. I can pick 0, right? 0 is in between negative root 2 and positive root 2. So then I'll plug that into my derivative. So f prime of 0 equals, remember, here's my derivative. Oopsies, no, I meant to pick this. There's my derivative. So that's what I'm going to plug it into. So I get, oopsies, I get negative 0 squared over square root of 4 minus 0 squared plus the square root of 4 minus 0 squared. Okay. Well, this first term, because you have a 0 in the numerator, is just going to go to 0 plus square root of 4, which is 2. Okay. Remember, when the square root's actually in the function, we just assume that the answer is going to pop out. The answer that it'll pop out is positive. But when you're solving an equation, so hopefully we see the difference between these two things. This is me solving an equation, and when I solve an equation, you have to think about both the positive and the negative root. If I'm just plugging a number into my function, the square root function will automatically return just the positive value. Okay? So I end up with a value that is positive, which means that I am increasing over this interval because my derivative, right, because f prime was greater than 0. Okay, so I'm increasing for that middle interval. Now I have to look at my interval on the right and my interval on the left. This one's a little harder to pick points, but let's just go ahead and pick 1.9 and negative 1.9. Okay. So if I plug these in, f prime of, I'll start with the positive one. I get negative 1.9 squared over the square root of 4 minus 1.9 squared, plus the square root of 4 minus 1.9 squared. Now, to save us some calculation, let's just think about what this will give me. Because remember, all I care about is whether this is going to be positive or negative. This right here, this piece right here, is going to give me a very small positive value, right? 1.9 squared is almost 4. So I'm going to have 4 minus something that's almost 4. Then I'm going to square root. So it's going to give me a positive value that's pretty small. Okay? So this will give me a small positive value. Okay? We'll take a look over on the left side. On the left side, this is guaranteed, the numerator is guaranteed to be negative. And then the denominator, like we said, is exactly the same as this other term. So it's going to give me a small positive value. Therefore, overall, if you have a fraction where the numerator is negative and the denominator is positive, you end up with a negative number. But more importantly, because the denominator is going to be really small, what does that mean about your number? Your number is going to end up being, this overall number is going to be end up being large, because the denominator is going to end up being small. The smaller your denominator, the larger your number. Okay? So I have a large negative plus a small positive. What does that tell you about your number? This is going to be less than 0. This value is going to be less than 0. Well, guess what happens when I plug in? Let me update this. So that means I'm decreasing over this interval. Okay. Well, guess what happens when I plug in negative 1.9? You'll notice if I come back and look at my derivative, anytime I plug in x, let me use a different color. Anytime I plug in x, no, let me use a different color. Anytime I plug in x, I'm squaring it, right? Do we see that? Anytime I plug in x, I'm squaring it, which means, does it matter whether my number is positive or negative? No. If I plug in a negative value, I'm going to get the same exact output that I would if I plugged in a positive value, because I'm squaring the number whenever I plug it in. Okay, so my derivative at negative 1.9 is actually the same as my derivative at positive 1.9, which means it's less than 0. So my function is also decreasing over this interval. Okay. Now, of course, if you have a calculator, if this confused you, like, oh, small positive, large negative, small positive, if this confused you, if you have a calculator, just plug in the numbers, okay, and see what you get out, right? That's the easiest way to do it. The reason why I did it this way is to show that you can also reason through it just to decide whether it's going to be positive or negative. That's all I really care about, is whether it's positive or negative. Okay, so we now have our intervals where I'm increasing or decreasing. So let's just write those down real quick. Okay, so first, increasing. Where am I increasing? I'm increasing from negative root 2 to positive root 2. One interval, that's it. Just that middle interval. Okay. Second question. Where am I decreasing? I have two intervals. I'm decreasing from negative 2 to negative root 2. And, so I can use this cup symbol to show that either of these intervals work, from positive root 2 to positive 2. So I had two intervals where I was decreasing. Okay, next. Question 3. Let's see, let me just make sure I got maximums. Do I have any local maximums? Well, take a look at that number line and tell me. Remember, a maximum represents if my function's increasing and then decreasing. So sure enough, that happens at root 2. So I have a local maximum at x equals root 2. And to be able to figure out what the corresponding y value is, of course, you could just plug it into the function, right? So my y value is just f of root 2, right? Just plug it into the function to see what you get for the y value. Okay? Question 4, local minimums. Do I have any critical points where my function is decreasing, right? So maximum is increasing, then decreasing. Do I have any critical points where I'm decreasing and then increasing? Look at my number line. Absolutely. Negative root 2, right? My function is decreasing and then increasing. So I have a local minimum at x equals negative root 2. And then, of course, to find the corresponding y value, you would just plug in the value into your function. Okay, question 1 through 4, done. We have answered those questions. Remind me, what test did we use? Well, since we haven't even touched the second derivative, we used the first derivative test to test these critical points. Okay, so let's keep going. To answer questions 5, 6, and 7, I need the second derivative. So let's start by solving for the second derivative. Okay, so where do we leave off? Okay, we have to pause on answering the rest of the questions because now we need to figure out the second derivative. So my first derivative, let me just copy it down from what we had before, was negative x squared. And to do ourselves a favor, I'm going to go ahead and write it back into power function form. So 4 minus x here, that was weird. 4 minus x squared to the negative 1/2, right? Because it's in the denominator. So that's that first term plus 4 minus x squared to the positive 1/2. Okay. So this derivative's a little bit longer, okay? And I can use so for this first term, I'm going to need to use product rule. But there's two terms to this function, so I can't forget about the second term once I'm done. So let's go ahead and consider product rule for this first function, or for this first term. Okay, my first function is negative x squared. My second function is 4 minus x squared to the negative 1/2. I need the derivative of both of those. So f prime is negative 2x. G prime is, well, G prime requires chain rule again. So I get negative 1/2, 4 minus x squared to the negative 3/2. Okay. Times the derivative of my inside function, which is negative 2x again. Okay, so now I can start putting this all together. So my second derivative is equal to, for this first term, once again, it requires chain rule, it requires the product rule. So I'm going to go ahead and put this all together. I get negative x squared times this whole term. Well, I'm going to go ahead and do some simplifying here. Negative x squared times negative 2x gives me 2x squared, 2x cubed. But then I have this, but then I have another negative. Whew, total, how many negatives do I have when I multiply these two functions? I've got a negative here, and a negative here. So 3 negatives my answer is going to end up being negative. I also have a 2 here and a 1/2 right here, and so those 2's are going to cancel out. Okay? So, what am I left with? I'm left with negative x cubed over 4 minus x squared to the 3/2. I could write that as cubed square root, but I'm just going to leave it like that to save us some time and energy here. So let's see. That's just that first term. So now I'm going to do the second half of product rule and multiply those two terms. That gives me negative 2x times 4 minus x squared to the negative 1/2. Okay. But then I still need to take the derivative of this term. Well, that one's just simple chain rule, and I'm left with 1/2 4 minus x squared to the negative 1/2 times the derivative of the inside function, which is negative 2x. Okay. Ooh, boy. Okay. Let me clean this up just a little bit more. Okay. And because there's so many common terms, okay, I end up with the following. I end up with 2x times 4 minus x squared to the negative 1/2 times x squared minus 6. Okay. Whoo-wee. So where do I go from here? Questions 5 and 6 are all about concavity. Where is the function concave up, concave down? Well, just like earlier, in order to really pick out those intervals, it's helpful to know where it's going to switch. So what I'm actually going to do is I'm going to actually try and find the inflection points first. To find the inflection points, I do something very similar to what I did with the first derivative. I'm going to set this second derivative equal to 0 and solve. Okay, well, what's nice is I've actually already, we've already factored this, which makes it fairly straightforward for finding these factors. So, first of all, if I look at this term, that tells me 0 is one of my solutions. If I look at this term, you might think, oh, 2 is one of your solutions. But remember, 2 is my endpoint. So I don't need to worry about 2 and negative 2. I don't need to worry about 2 and negative 2 because those are my endpoints. So I don't need to stress about that one. Last but not least, what about this one? If I solve for this, I get x squared equals 6, and x is equal to the positive or negative square root of 6. Well, guess what? Square root of 6 is greater than 2, which means this is not in my domain. And same thing with negative root 6. Negative root 6 is less than negative 2. So these numbers are not in my domain. Whew! That means I don't have to worry about them. So the only possible inflection point I have is x equals 0. Okay. So now what I can do is I can do a similar process that I did with the first derivative, is I'm going to make a number line over my domain with this point on it. Okay? Because that point represents where my concavity could possibly switch. And now I'm going to test my concavity in each of these intervals. So I'm going to pick a number in each of these intervals and test the concavity. Which derivative do I use to test the concavity? The second derivative. Okay, so I'm going to go ahead and plug in negative 1 to my second derivative. What does that give me? That gives me 2 times negative 1 times 4 minus negative 1 squared to the negative 1/2 times negative 1 squared minus 6. Okay. Once again, I only care about whether this is positive or negative. So what I can do is I can just look at the factors and determine what's going to happen with each of my factors. This factor, negative. 2 times negative 1 is negative. This factor, negative 1 squared is just positive 1. 4 minus 1 is 3. And the root of 3 is still going to be, remember, roots always will input out a positive value. So that's just positive. Last but not least, negative 1 squared minus 6. Well, negative 1 squared is positive 1, but 1 minus 6 is going to give me negative 5. So that's going to give me a negative value. So I have 2 negative terms and 1 positive term. That means overall, my function is, I'm skipping a step. That means this is going to be positive, right? 2 negatives make a positive. So overall, my second derivative is positive, which means I'm concave up. Well, now let's plug in positive 1, see what happens. Okay, f double prime of positive 1 equals 2 times positive 1. 4 minus positive 1 squared to the negative 1/2, and positive 1 squared minus 6. Okay, well, this one obviously is now positive, but then if I look at the other two, remember, the other two, I was squaring my input, which means it doesn't matter whether I plug in a negative 1 or a positive 1, I'm going to get the same result. So this one's still going to be positive, and this one's still going to be negative. Overall, it's less than 0 because you have 2 positive terms and 1 negative term. So, negative means my function is concave down. So, I'm now ready to answer questions 5, 6, and 7. Ready? Let's see, what color did I leave off on? Blue. Question 5. Where's my function concave up? It's concave up on the interval -2 to 0. Okay. Question 6. Where's my function? No. There we go. 6. Where's my function concave down? On the interval 0 to +2. And finally, question number 7. Does my function have a point of inflection? It absolutely does, right? Remember, points of inflection are where the graph switches concavity. And in our case, it switches concavity at x equals 0. Okay. Perfect. Okay, so there's quite a few problems on your homework where it has you do this exact thing. Find all 7 of these criteria, okay? And then I think it has you sketch the graph. So go ahead and try this out, and then we'll finish off by sketching this graph based off of what it gave us. So now that we've come up with now that we've answered these 7 different questions about this function, this allows us to actually draw a graph, or at least sketch a graph, a rough approximation of what this graph looks like. So I know that my function only exists between -2 and +2. Okay? And I know that my function is increasing. Well, actually, it's pretty obvious, actually, if I plug in +2 or -2, I end up getting 0. So I know that my function starts at this point and it ends at this point. Well, let's see, my function is decreasing based off of question 2. My function is decreasing from -2 to negative square root of 2. So from this point to this point, my function is decreasing. Okay? But then from negative square root of 2 to positive square root of 2, my function is increasing. Okay, so I know that I'm increasing. I'm going to eventually increase as I go up that way. But let's be careful here, because I also know that my function is concave up from negative 2 to 0. So as I continue to graph this, I have upwards curvature up until I reach 0. And I think we go through the point 0, 0. Because if you come back to this graph, what happens if I plug in 0? This term right here is going to cause my function to just equal 0. So I have upwards curvature all the way up until I hit x equals 0. And then after that, I have downwards curvature until I reach my maximum at positive square root of 2. And after I hit my maximum, I then decrease, but I still have this downwards curvature all the way until the end of my function. Perfect. So based off of everything that we were able to calculate, based off the answers to those 7 questions, I can now sketch the graph. Okay, another long video today, but hopefully this helps you feel a little bit better with the homework. Please, 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 this homework can be pretty intense. So if you have any questions or run into any issues, please let me know, and I'm happy to help. Have a great day.